And then what I get is I can identify, this fellow is going to be the energy term because we have E psi. This fellow is going to be the potential energy term, which is half kx square, right? Minus h square by 2m. So 2me by h square. H cross square, sorry. Thanks. Now we've switched from mass to mu. Good. And over here also I'll have the same thing. 2. So 2 and 2 cancel out. 2 mu by h cross square, right? Tell me if I'm making any mistake out here. So what I get is that alpha is equal to 2 mu e by h cross square, and alpha square is equal to, what happened to the minus sign? I think that is conserved. Okay. This goes on the right side, so it becomes, yeah, fine. Mu k by h cross square. Right? And I know that omega is equal to square root of k by mu in this case, not m. So I substitute all this, and I am not calculating it because I really remember this energy very well. E is equal to half h cross omega. Right? Violating the quantization of energy. Why? There is no photon. You are doing it for particles. You are doing it for matter. Right? But what you are saying will realize how the photon comes in. Okay? Just give me another few minutes. Right? That's my ground state energy. Okay? And for the vibrational states, we normally use the ground state as 0. The more general solution is written like V plus half h cross omega. So what I have is a series of energy levels which are all spaced equally apart, and the spacing is h cross omega, and if any photon is absorbed, then the frequency of the photon will be omega by 2 pi or nu. Right? So I don't absorb half a photon. In fact, any of these, all of them are h cross omega. And V goes from 0, 1, 2, so on and so forth. Now, you think about the lowest possible energy over here, which is known as the ground state energy, or also known as the 0 point energy, because that is the energy that survives when you go down to 0 Kelvin also, that quantum mechanical energy. That's half of h cross omega. So, if you think about classical mechanics, and I think about the spring, then it can have 0 energy. It's stationary? No. The quantum mechanical particle cannot have a 0 energy. It can't be stationary. It has to vibrate. Because if it's stationary, exactly, you get to know the position of this particle, which is not allowed. So it has to vibrate. And that's my 0 point energy. or ground state energy or 0 point energy, whatever. Right. So if I were to plot these energies, let me make a scale over here, and let me plot this energy. First, let me make the potential energy as half kx squared. So in this scale, this is my x, and that's energy E. So let me make this potential, which is a parabola, and goes to 0 as x goes to 0. Right? So that's my potential energy. And if I wish to plot the energy half of h cross omega, then that might come somewhere over here, a little bit above from 0. Right? And that's quite interesting. If you now think about the wave function, the wave function is e to the power minus alpha x squared by 2. First of all, is it a well-behaved wave function? Yes? It goes to 0. Okay. But it goes all the way to infinity and minus infinity. So it's essentially decaying. Yeah? As a square of x. E to the power minus x squared. Alpha is a constant, I guess. No? 2 mu E by h cross squared. They are all constants. Energy is also half h cross omega in this case. So, if I were to plot this wave function, then that's kind of a decay. And see, this is the energy axis, but I'm just plotting the wave function. So this is also the wave function axis. Okay. Of course, I cannot equate the two. Okay, don't make that mistake. To equate energy and wave function. But now there's something to think about. What are these points? These 2 points that I have marked in purple. Here, the total energy E is equal to the potential energy. Right? At that particular distance x, which will be of course symmetrical because the parabola is symmetrical. This is the horizontal line of energy, and this is my x-axis. So at that particular x, half kx square is equal to E. When does this happen in a classical harmonic oscillator? At the extrema. The amplitude cannot be larger than that. Right?